We're going to cover chapter 5.2 through 5.4. We're going a little further into the chapter on gases. And we've already talked about the relationship between the pressure, the volume, and the temperature of the gases and learned about the combined gas law. We actually learned about Boyle's law, Charles' law, and Gay-Lussac's law, which we combined into the combined gas law equation, and that's all we need for those changing gas problems. Now we're going to bring in the actual amount of gas in, and that's going to give us the ideal gas law equation. You see it right there, PV equals nRT. We'll talk more about that when we get there. And then we're going to talk about the set condition called standard temperature and pressure, and at a given temperature and pressure there's a direct relationship between the volume of the gas and the number of moles of gas, and we'll talk about that when we get there. And then we have some other gas law calculations, which include calculating the density of a gas and the molar mass of a gas. We're finishing off then with stoichiometry. We have a new way to get to moles. Having a new way to get to moles, we have a new way to enter into stoichiometric calculations. Okay, let's go ahead and get warmed up. And we're asked to write a balanced equation for the following reaction in an acidic solution. And before we begin, I want to remind you that at any time you might want to pause the video, come up with your own answer, and then continue with the video to see how I got the answer. But it's good for you to be practicing these things, not just watching me do them. You need to practice them yourselves. And in a normal classroom, I would stop and give students the opportunity to do some of these on their own. Okay, so let's go ahead and do this. And we have our first step of splitting our equation into two half reactions, one into oxidation and one for reduction. And so let's identify what's going on with the nitrogen and the manganese. We know the oxygen is always going to be -2, so we're not expecting it to be oxidized or reduced. Okay, so what's the oxidation number of manganese in the permanganate ion? So we're going to ask what plus 4 times -2 is equal to -1, or what minus 8 is equal to -1, and 7 minus 8 is -1, so the manganese is +7. You might write that down, either above or below the manganese in permanganate. Then on to the nitrogen and nitrite. And what is the oxidation number of the nitrogen? Well, what plus 2 times -2 is -1, or what minus 4 is -1? And that would be +3. So write +3 above or below the nitrogen symbol in nitrite. In manganese 2 on the right, well, there is your oxidation number, +2. And now what about the nitrogen and nitrate? What's the oxidation number here? Well, what minus 6 is -1? +5. So the nitrogen went from +3 to +5. It lost electrons, and so it underwent oxidation. The manganese went from +7 to +2. It gained electrons, so it underwent reduction. Okay, there was step 1, splitting our equation into two half reactions. Step 2 has 4 substeps, beginning with step 2a, which is to balance the element being oxidized or reduced. So in the oxidation, 1 nitrogen on the left and on the right, so that's balanced. In the reduction, 1 manganese on the left and on the right, so that's balanced. Step 2b is to add electrons in order to balance the oxidation number, and that nitrogen went from +3 to +5. It lost 2 electrons, so +2 electrons on the right. In the reduction half reaction, the manganese went from +7 to +2. It gained 5 electrons, so add 5 electrons to the left. Step 2c is to now balance the charge, and we're in an acidic solution, so that means we're adding H+, hydrogen ions, H+. Since we're adding positives, well, we need to add that to the side that needs more positives. Okay, let's look at the oxidation half reaction. We have 1 negative on the left and 3 negatives on the right. Since I'm adding positives, I need to add 2 positives to the right. Now I have -1 balancing -1. In the reduction half reaction, I have 6 negatives on the left and 2 positives on the right. So it looks like I need 8 more positives on the left. Step 2d is to add waters in order to balance the oxygens. I need 1 more oxygen on the left in the oxidation half reaction, and 4 more oxygens on the right in the reduction half reaction. And now my two half reactions are balanced. Step 3 is to now add these two half reactions together so that the electrons cancel. In the first reaction, I have 2 electrons on the right, and the second 5 on the left. These need to be the same number, so the least common multiple says that number is 10. So I'm multiplying equation 1 by 5 and equation 2 by 2. That gives me 5 nitrites, 5 waters, 2 permanganates, and 16 hydrogen ions on the left, 5 nitrites, 10 hydrogen ions, 2 manganese 2 ions, and 8 waters on the right. I have both waters and hydrogen ions on the left and on the right, so I subtract the smaller of these numbers from each side, and that's going to cancel the waters from the left and the hydrogen ions from the right, leaving me with 6 hydrogen ions on the left and 3 waters on the right. And there's my final balanced net ionic equation. Okay, same problem, same approach. We split into our 2 half reactions first. And let's see, what's the oxidation number of chromium in chromate? Well, what minus 8 is negative 2? Positive 6. So write plus 6 with the chromium. What is the oxidation number of sulfur in sulfite? Well, what minus 6 is negative 2? And that's positive 4. So write positive 4 with the sulfur. Over on the right, the chromium's plus 3. There's its oxidation number, so write plus 3 with the chromium. And what about the sulfur? What minus 8 is negative 2? And that would be positive 6. Okay, so sulfur went from plus 4 to plus 6, so it's undergoing oxidation. The chromium went from plus 6 to plus 3, so it's undergoing reduction. Step 2a is to balance the element being oxidized or reduced, and I have 1 sulfur on the left and on the right, and 1 chromium on the left and 1 on the right. Very often there's nothing really to do in step 2a. Step 2b is to add electrons in order to balance the oxidation number. And sulfur went from plus 4 to plus 6, it lost 2 electrons, so plus 2 electrons on the right. Chromium went from plus 6 to plus 3, so it gained 3 electrons, so 3 electrons show up on the left. Step 2c is to add hydrogen ions to balance the charge, and in the oxidation half reaction we have 2 negatives on the left, 4 negatives on the right. I need to add 2 positives to the right, so I have negative 2 balancing negative 2. In the reduction half reaction, I have negative 5 on the left and positive 3 on the right. Since I'm adding positives, I need to add 8 positives to the left. So I have positive 3 balancing positive 3. Then we add waters to balance the oxygens. And in the oxidation half reaction, I need 1 more oxygen on the left. In the reduction half reaction, I need 4 oxygens on the right. And note that took care of the hydrogens as well. Now we add these 2 half reactions together so that electrons cancel. In the first reaction, the first equation, I have 3 electrons on the right, and the second I have 3 on the left. The least common multiple of 2 and 3 is 6, so I'm multiplying equation 1 by 3 and equation 2 by 2. This time I'm going to go ahead and write out the waters and the hydrogen ions on both sides. And then reduce both sides by the smaller number so that I can eliminate spectators. Again, that's what we're doing here. We're eliminating spectators. And this is my final balanced net ionic equation. Okay, a gas subtle in a flexible container occupies 1.25 liters at 122 degrees C and 0.831 atmospheres. If the temperature is held constant, find the pressure when the volume is 1.71 liters. Okay, we have a changing gas law problem, and we only need one equation, the combined gas law equation. P2 times V2 over T2 equals P1 times V1 over T1. I hope it's easy to remember. P and V on top, T on the bottom. One side has the 2's, the other side has the 1's. And we have a constant pressure, so we can scratch those out. And at this point, we have Boyle's law. We didn't need to remember it as a separate equation, because it came right out of our combined gas law equation. Okay, we're after the new pressure, so let's divide out V2. And here's P2 isolated. We have these 3 variables, and we can go ahead and plug them in. All units cancel but atmosphere, leaving me with a reasonable unit. Is the number reasonable? We'll have a decrease in pressure. Does that match an increase in volume? Yes, it does. So we can have confidence in our answer. Again, we should be always asking, does our answer make sense? Okay, a gas sample in a flexible container occupies 725 milliliters at 250 degrees C and 1 atmosphere. If the pressure is constant, find the volume when the temperature is 22 degrees C. Okay, we have a changing gas law problem again, and so our combined gas law equation still. And this time the pressure is constant, so we can eliminate the pressure, and that actually gives us Charles' equation. We're after the new volume, so we're going to multiply out T2. And now our equation is isolated for the variable we're after. We just need to plug everything in, and remember that make sure that your temperatures are always, always, always in kelvins. And when I put this on my calculator, all units cancel and I get 409 milliliters. Should I have had a decrease in volume? Yes, a decrease in volume matches a decrease in temperature. So I can have confidence my answer seems correct. I can't know for sure that it's correct, but at least I know I haven't made any gross errors. Okay, a gas sample in a rigid container. Remember, rigid means a constant volume of 2.50 liters at 425 degrees C has a pressure of 10 atmospheres. If the temperature is reduced to 85 degrees C, what is the new pressure? Again, we have a changing gas law problem, so again we use our combined gas law equation. P2 times V2 over T2 equals P1 times V1 over T1, and the volume is constant, so we can eliminate the volume, and that gives us Gay-Lussac's equation. We're after P2. Let's multiply out T2, and there's P2 isolated. Once again, for temperatures, these need to be in kelvins. And note, all units cancel but atmospheres. Should I have had a reduction in pressure? Well, I had a reduction in temperature, so yes, I should have a reduction in pressure. Next, we have a gas in a flexible container, which occupies 1 liter at 0 degrees C and 712 torr. Find the pressure when the temperature is 1150 degrees C and the volume is 1.13 liters. Okay, again we have a changing gas problem. So it's the same gas, we just changed the conditions, and so we're using our combined gas law equation. And let's see, anybody held constant this time? No. So we're after what? We're after the new pressure. So we get P2 by itself by dividing out V2 over T2. Of course, we get rid of that by multiplying in the reciprocal, T2 over V2. And now we have everything that we need. Let's make sure we plug in the right variables for these, for each of these. And again, also make sure that your temperatures are in kelvins. And I can see that all units cancel, but the appropriate unit of torr, and my pressure went up greatly. Well, I had my temperature go up greatly. So that actually does make sense. My volume went up a little, but my temperature really went up a lot. So yes, my answer does make sense. Okay, a gas in a flexible container occupies 128 liters at 225 degrees C and 921 torr. Find the volume when the temperature is 22 degrees C and the pressure is 572 torr. Okay, I think this time we're going to use our units. And so remember that, that three-step procedure. Step one, we identify, well, or should I say we recognize that we're after V2, and V2 must get its units from V1. In step two, the other factors affecting the variable, this situation, must have their units cancel, and so I put one over the other. In other words, P over P and T over T. Step three is where we actually have to stop and think more about it. Is that my new P on the top or my old P? Is that my new T on the top or my old T? So if I increase my pressure, do I increase my volume? No, increasing my pressure decreases my volume, telling me that the new pressure goes on the bottom. Then temperature. If I increase my temperature, do I increase my volume? Yes, I do. So they're directly proportional, and the new guy goes on the top. Now we just need to plug everything in. And again, all those temperatures need to be in kelvins. And the pressure units were the same. Sometimes we have to change one pressure unit into another. Note all units cancel, but the answer must be the unit of liters. And my volume didn't change a whole lot. Well, my pressure went down by quite a bit, while my temperature went up by quite a bit, and so they kind of balanced each other out or neutralized each other out. So that does seem reasonable that I wouldn't have a whole lot of a change. Okay, a gas in a flexible container occupies 625 milliliters at 25 degrees C and 0.912 atmospheres. Find the temperature when the volume is 125 milliliters and the pressure is 5.72 atmospheres. We're going to use our units again. So T2 must get its units from T1. The other factors affecting the system are volume and pressure. So P over P and V over V. And now, if I increase my pressure, would that increase my temperature? And that doesn't really sit well with me, so I ask it the other way. If I increase my temperature, does it increase my pressure? Yes, it sure does. So the new guy goes on the top. If I increase my volume, does that increase my temperature? Again, that doesn't sit well with me, so I ask it the other way. If I increase my temperature, do I increase my volume? Yes, it does. So the new guy goes on the top. And the great thing about using this technique is not only did it give us an equation we may have not remembered, but it also gives it to us in the form where it's already isolated for the variable that we're after. Okay, we just need to plug everything in. And all units cancel, but kelvins. And we had an increase in temperature. Does that match the data? Well, we had quite an increase in pressure, but also a decrease in volume. So yes, it does match. Okay, on to new material, and we've already seen the relationships between pressure, volume, and temperature in Boyle's law, Charles' law, and Gay-Lussac's law, and the combined gas law equations, which we just went through using some. And now we want to bring in the amount of gas. So let's hold the pressure and temperature constant and ask what would be the relationship between the volume of a gas and the number of gas molecules. And I think we know that it's going to be directly proportional. Think about blowing up a balloon. As you're adding gas, the balloon is getting bigger. Okay, so that tells us that the volume is proportional to the number of gas molecules. And we know that the pressure times the volume over the temperature was equal to a constant. And since the volume is proportional to the number of gas molecules, then PV over T is proportional to the number of gas molecules. And now let me put all these variables in the numerator, and so the pressure times the volume is directly proportional to the number of gas molecules times the temperature. And I think you know where we're going with this next. We just need to bring in a constant, a proportionality constant. And here we have what's called the universal gas constant, R. It's called the universal gas constant because it doesn't matter which temperature, what volume, what pressure. R, in this case, accounts for all four variables. And it has this value of 0.0821 liter atmospheres per mole Kelvin. And yes, we need to pay attention to those units. We're actually going to use those units to set up our calculations for us. So even if you like using equations, I hope that you're learning to use units so you have another tool to add to your toolbox. If there's anything you should learn from this course, it's how to use units. Okay, let's look at the calculations that we're going to be doing, and we're still going to have our normal step one, identify what you're after and write it down on the far right, so that's always the same. Actually, in every example, that's always been the same. Step 2 is going to be a little bit different because we're going to start with the universal gas constant with the unit that we're after in the numerator. So if we're after liters or atmospheres, we're going to use it straight up. However, if we want moles or kelvins, we're going to invert it. So we would then have mole kelvins over that 0.0821 liter atmospheres. Then we need to, then at that point it tells us where the other variables go. So let's say we're after liters. Well, then that would tell us atmospheres needs to cancel, so that would go on the bottom. Moles and kelvins need to cancel, and so they would go on the top. So at this point, we know where everybody else goes, and it essentially builds our equation for us. And as it normally does, would be isolated for the variable that we're after. Okay, let's do an example. We're told a good liter blimp holds 5.91 million liters of helium at 27 degrees C and 1 atmosphere. How many moles of helium are in the blimp? Okay, we're using our units, and we always have the step 1. That's never changed no matter what variant of units that we use. And we're after moles. Now, because we're doing a gas law problem for step 2, we're going to start with our universal gas constant. Actually, you might start by throwing out a large denominator line, and then start with the universal gas constant with the unit we're after in the numerator. So in this case, moles and Kelvin are in the numerator, and the 0.0821 liter atmospheres are in the denominator. At this point, I can see what needs to cancel and how they need to cancel. I need to put my temperature in kelvins on the bottom, my volume in liters on the top, and my pressure in atmospheres on the top. And now note how all those units cancel but the appropriate unit of moles. Then I bring in the numbers, and only after I have the numbers in, I would go and scratch out those units that cancel. So scratch the K's, scratch the L's, scratch the ATMs, circle the mole, just to make it jump out just that much more that we've done this correctly. And when I put this on my calculator, I come up with 240,000 moles of helium. That's a lot of helium, but the Goodyear blimp's a pretty big thing. Okay, I want to introduce you to standard temperature and pressure, where standard temperature and pressure are 0 degrees C and 1 atmosphere of pressure. When we're at standard temperature and pressure, STP, then there is a direct relationship between the number of moles and the volume of the gas. Let's go ahead and derive that ratio. And so I'm going to take my gas law problem and get the volume of 1 mole. So step 1 equals liters, step 2, start with liters in the numerator, step 3, place all the other units across the denominator line, and then put in the numbers, scratch out the units, circle the one that's left, and what we're seeing here is 1 mole of gas at STP has a volume of 22.4 liters. So there's our molar volume at STP, giving us the 2 conversion factors, 22.4 liters per mole, or 1 mole per 22.4 liters. Now the downside is this is only relevant at standard temperature and pressure. So if we are at some other temperature or some other pressure, don't try to use a shortcut because it's not going to work. It's not going to have the right number. Now it would have another number, and that's essentially something I want to point out. If we had a different temperature and a different pressure, we would still have a constant ratio between the volume and the number of moles of that gas. It would just be a different number. Okay, let's look at an example where we're asked how many moles are contained in 125 liters of oxygen at STP. Well, for this we're actually using our normal unit analyses approach. So step 1, we're after moles of oxygen. And step 2, we would start with that 125 liters of oxygen. And our normal step 3, let's get out of that initial unit, so out of liters of oxygen. And now the big question, can we go straight from liters of oxygen to moles of oxygen? And the answer is yes, since we are at STP. If we weren't at STP, we'd be needing more information, like the temperature and pressure. And this also means we need to remember that number, 22.4 liters per each mole. And hence 5.58 moles of oxygen. So again, when we have STP, we can use our normal unit analyses approach. Not at STP, we're using this new gas law type unit analyses approach. Okay, what is the volume of 2.5 moles of hydrogen? And again, this would be at STP. If not, we'd be kind of sunk. Okay, step 1, we're after the volume, so liters of hydrogen. Step 2, of course, we start with the 2.5 moles of hydrogen, recognizing this is a normal unit analyses approach. And step 3, out of moles of hydrogen. Can we go straight from moles of hydrogen to liters of hydrogen? And since we're at STP, the answer is yes. And again, the molar volume at STP is 22.4 liters per each mole. So that 2.5 moles takes up 56.0 liters of volume. Okay, some examples of some calculations that we can do with the material we've just learned, essentially the universal gas constant, includes the molar mass of a gas. So we're asked, what's the molar mass of gas A? Well, ultimately, the pressure, the temperature, and the volume leads us to moles. So if we were given the mass of the gas, then we could put the mass over that number of moles. Let me show you an example where we have a sample of liquid acetone placed in a 3-liter flask and vaporized by heating to 95 degrees C at 1.02 atmosphere. The vapor filled in the flask at this temperature and pressure weighs 5.87 grams. What is the molar mass of acetone? We're using our units, at least our gas law variant of units, starting with step 1, we're after grams per mole. Fortunately, step 1 never changed. Step 2 changed because when we're using gas law information, we're going to throw out that big denominator line. And first I'm going to ask, how do I get grams? And that's from the given mass, 5.87 grams. Now how do I get moles? Well, that's from my universal gas constant with moles in the denominator. And here we can see grams and moles, so the liters, the atmospheres, and the kelvins need to cancel. So we place those units across the denominator line. And then let's put in the temperature in kelvins, the volume in liters, and the pressure in atmospheres. Once the numbers are in, I would scratch out those common units. So scratch out atmospheres, scratch out liters, scratch out kelvins, circle the grams over moles, just to make it jump out that much more that we've done this correctly. And when I put this on the calculator, I come up with 58.0 grams per mole. There's the molar mass of acetone. Another calculation we can do is to calculate the density of gases, and often it seems like information is missing because one of our data points happens to be the molar mass of the gas. Let me illustrate this with an example. We're asked to calculate the density of nitrogen gas, so that's N2, at 27 degrees C and 1 atmosphere. At first glance, it looks like we don't have enough information. We only have the temperature and the pressure. Well, let's start with our units and see how this goes. Step 1, we're after the density of a gas. So the density units for a gas are grams per liter. This is a gas law problem, so that means we're going to use this new variant of unit analyses, and that begins with throwing out that big denominator line and then asking about the numerator. How do we get grams? Well, that's actually going to come about from the molar mass, which we get right off the periodic table. So remember, nitrogen is N2, so twice 14.0 for 28.0 grams per each mole. Then, how do we get liters? From the universal gas constant with liters in the denominator. And now we can also see how moles already canceled. And so I just need to cancel out kelvins and atmospheres by placing them across the denominator line. Let me go ahead and put in my pressure in atmospheres and my temperature in kelvins. And I calculate a density of 1.14 grams per liter. Real quickly, I would point out, looks like we didn't have enough information. The reason we didn't have enough, it looked that way, is because we did have that molar mass coming from the periodic table. Okay, we're going to revisit stoichiometry because we have a new way to get to moles. We just saw a new way to get to moles from our universal gas constant, or from the ideal gas law. If you want to use equations, I hope you're using your units and learning a new tool. But just like any other stoichiometric problem, if we're given a balanced equation or given an unbalanced equation and we balance it, then we might be asked about how much of one reactant reacting with another, or product formed, or something of that nature. Let's look at an example here where ammonia is produced by the reaction here. And we're asked how many liters of ammonia at standard temperature and pressure can be formed when 50 liters of nitrogen at standard temperature and pressure react with excess hydrogen. Okay, well, since it's excess hydrogen, we don't have to worry about this being a limiting reactant problem. And since both of the gases are at STP, we can use our normal unit analyses approach, meaning our normal step 1, what are we after? Liters of ammonia. And our normal step 2, we're looking for a number with a single unit to start the calculation with, which would be the 50 liters of nitrogen. And now on to step 3, let's get out of that initial unit, so out of liters of nitrogen. And then comes the big question, can I go straight from liters of nitrogen to liters of ammonia? No, the only way to relate one chemical to another is through moles. So first from liters of nitrogen into moles of nitrogen, and I can do this in one move since I'm at STP. And then from moles of nitrogen and into moles of the ammonia. And then from moles of ammonia, we can go straight to liters of ammonia, again, just because it's at STP. If it wasn't at STP, there'd be a lot more work involved. Molar volume was 22.4 liters per each mole. Molar ratio, 2 moles of ammonia from 1 mole of nitrogen. And again, 22.4 liters per mole. So we can see we don't even need to put that on our calculator, just simply 50 times 2, or 100 liters of ammonia. Okay, next, ammonia is produced by that same reaction, and now we're asked how many liters of hydrogen at 25 degrees C and 1 atmosphere, not STP, are needed to react with 918 liters of nitrogen at 0 degrees C and 1 atmosphere. This is STP. Okay, but we're given 2 reactants, so it's a limiting reactant problem, but fortunately, at least one of them is at STP, so that's going to minimize our work at least a little bit. Okay, our primary equation, and you should always start with your primary equation, the one that gets you what you're after, how many liters of hydrogen. Well, actually, it's not a limiting reactant problem since they're acting about one reactant to react with another, excuse me. So step 1, we are after liters of hydrogen, but this isn't at STP, so we have to use our gas law approach to units. So there's my big denominator line. And I'm going to get liters from the universal gas constant used straight up. And that tells me where my pressure in atmospheres, my number of moles, and my temperature in Kelvin need to go. Let me go ahead and, oh, I don't have my number of moles. I'm going to get that from the nitrogen information. So let me use another unit analysis setup. I'm after moles of hydrogen. Now, since this is at STP, I can use my normal step 2 and start with that 918 liters of nitrogen. And then from liters of nitrogen, can I go straight to moles of hydrogen? No, again, I need to go into moles to relate one chemical to another, so into moles of nitrogen. And then from the balanced equation, we can go from moles of nitrogen to moles of hydrogen. And again, the only reason we could do this in this fashion is because this was at STP, where we know the molar volume of 22.4 liters per mole. And that does also mean you need to remember that number if you want to do this in this easy fashion. And what if you forgot that number? Well, then you just have to do it the long way, so the gas law way. So the big denominator line, put moles in the numerator, etc. Okay, and then from our balance equation, there's 3 hydrogens to 1 nitrogen, and hence 122.9 moles of hydrogen are needed to react, which we now plug in with the rest of the data into our primary equation. We'll scratch out all those units and circle the one that's left, just to verify that we've set this up correctly. And I come up with 3,010 liters of hydrogen. Does my answer seem to make sense? Well, that was nearly 1,000 liters of nitrogen, so yeah, that does seem reasonable. Okay, I want to talk about the ratio of volumes when we have 2 gases at the same temperature and pressure. When we have 2 gases at the same temperature and pressure, their volume ratios will be the same as their mole ratios, meaning the volume of 1 mole of gas will be the same as the volume of another mole of gas if it's at the same temperature and pressure. Let me remind you of this calculation we did earlier. And this was an example where we had 2 gases at the same temperature and pressure. And so those volume ratios canceled. Now what if you're not at STP? Well, those numbers wouldn't be the same as the 22.4 liters, but they would be the same as each other. And so they would cancel. And so ultimately, we have volume ratios that could serve in place of mole ratios. So I can go from liters of nitrogen directly to liters of ammonia. But again, this is only, and I have to say this again, only if we have both gases at the same temperature and pressure. Okay, let's practice some of the things that we've just learned. We're told a rigid container holds 3.79 liters of gas. If there are 2.23 moles of gas in the container at 1 atmosphere, then what is the temperature of the gas? Okay, we have a ideal gas law type problem because we see moles, so it's not a changing gas problem anymore. And we did all these using our units. You could use that equation, but I hope that you're not. I hope that you're using your units. I'm sure you've already mastered equations. You may not have mastered units. Let's make sure we have this second tool in our toolbox. Okay, so step 1, we're after the temperature, so kelvins. Now this is a gas law problem, so for step 2, we're going to start with that big denominator line and put the universal gas constant in with the unit we're after in the numerator. In other words, we have mole kelvins on the top to give us kelvins, 0.0821 liter atmospheres on the bottom. And that tells us where everybody else goes. I'm going to have to get out of moles by putting it on the bottom, liters and atmospheres by putting them on the top. And I have these 3 variables, so I'm going to go ahead and plug them in. And when I put this all on my calculator, I come up with 20.7 kelvins. Does my answer make sense? Well, that is tremendously cold, so I might double check myself, but do note, that's 2.23 moles. If this was at STP, that would be nearly 50 liters, but it's 3.79 liters, so actually that does make sense. That would be a very cold temperature in order to have this very small volume. Okay, a sample of an unknown hydrocarbon is placed in a 1 liter container and vaporized by heating to 90 degrees C at 1.524 atmospheres. The vapor filling the flask at this temperature and pressure weighs 7.974 grams. Calculate the molar mass of this hydrocarbon. Okay, we're using our units, and step 1, we're after grams per mole, molar mass. Now, we're using gas law information, so we're going to use this gas law variant. And so we're going to start with, and I'm going to throw out my big denominator line, Where am I going to get my mass unit of grams? From the given mass that was given. Where am I going to get the units of moles? From the universal gas constant, with moles in the denominator. And now that tells me where the other three variables go. The liters must go on the bottom so that it cancels. Same with the atmospheres. The kelvins must go on the top. Again, so that the liters, atmospheres, and kelvins cancel, leaving me with grams over moles. Let me bring out those numbers. And that 363.15 comes from, actually 0 degrees C is 273.15 kelvins. Since we're given 90.00 degrees C, I'm going to bring out those other two digits. And that gives us 156.0 grams per mole for this unknown hydrocarbon. And that answer is definitely reasonable. Okay, calculate the density of argon at 22 degrees C and 0.851 atmospheres. Okay, seems like there's not enough information given. Well, that's because one of these comes from the periodic table, meaning one of the data points comes from the periodic table. We are still using our units with the gas law variant. We're after the density, so grams per liter. And for step 2, we're going to start with that big denominator line. Where do I get grams? From the molar mass right off the periodic table. Where do I get liters? From the universal gas constant with liters in the denominator. And note, moles canceled, so we just need to have the temperature in kelvins and the pressure in atmospheres to complete the calculation. So now we can see why there was such a minimum amount of information given. Okay, that pressure in atmospheres is given. We need to convert 22 degrees C to kelvins by adding 273. And when I put this all in my calculator, I come up with 1.40 grams per liter. I might ask, does my answer make sense? And I'm going to say, yeah, there's a wide range of densities of gases, so it's hard to have a lot of confidence, but at least it's somewhat reasonable. Okay, ammonia is produced by the reaction below. And now, how many liters of ammonia at 25 degrees C and 0.910 atmospheres, not STP, can be formed when 100 liters of nitrogen at 25 degrees C and 0.91 atmospheres reacts, again, not STP, but they are the same temperature and pressure when it reacts with excess hydrogen. Yay, excess hydrogen means it's not a limiting reactant problem. Okay, now both these gases are at the same temperature and pressure, so we may remember that means that these gases relate through volume ratios equivalent to their mole ratio. And we are going to use our normal unit analysis setup. We're after liters of ammonia. And for step 2, which of these numbers are we starting with? The 100 liters of nitrogen. And now on to step 3, out of liters of nitrogen. Can I go straight to liters of ammonia? And we already recognized, yes, we can. We can use volume ratios equivalent to mole ratios. And from the balance equation, I see 1 nitrogen to 2 ammonias. And hence 200 liters of ammonia is produced from the 100 liters of nitrogen if it's at the same temperature and pressure. So it's kind of nice when we have two gases at the same temperature and pressure. It really simplifies our calculations greatly. Okay, same reaction, but this time we're asked how many liters of ammonia at 350 kelvins and 2.11 atmosphere, not STP, can be produced from 67.5 liters of nitrogen at STP, reacting with 181 liters of hydrogen at 398 kelvins and 6.12 atmospheres, so not at STP. Okay, where do we begin? Lots of stuff going on. Well, I hope we can see we have a limiting reactant problem. Yes, this time we really do. And how do we start? Well, we always should start by identifying what equation or what process, what procedure gets us the units we're after. And we're after liters of ammonia, and it's not at STP, so we're using our gas law variant of unit analyses. So still step one. Fortunately, that never changed even a little. We're after liters of ammonia. For step two, being a gas law problem, we're going to start with our big denominator line, and then how do I get liters of ammonia? From the universal gas constant used straight up. And that tells me where everybody else goes. Let me put my number of gas molecules in moles, my temperature in kelvins, and my pressure in atmospheres. Oh, but I don't have moles of ammonia. Well, that's what that information on the nitrogen and hydrogen is about. So first, we're going to use our units here. So after moles of ammonia, and we're going to get that, well, we do the nitrogen first, that's at STP, so we can use our normal unit analysis approach and our normal step two, starting with our number with the single unit. So the 67.5 liters of nitrogen. And then from liters of nitrogen, we go to moles of nitrogen. And again, we can only do this because we're at standard temperature and pressure. And then from moles of nitrogen, we can go to moles of ammonia. You need to remember that molar volume, that 22.4 liters per mole. If you forget, you're going to have to do this a long way. And the balance equation says 2 moles of ammonia formed from 1 mole of nitrogen. And so the nitrogen can potentially form 6.027 moles of ammonia. But we're not done. We can't put that in because we have to look at the hydrogen information. And this is not at STP. So we're going to do our normal step one. That's always going to be the same. But for step two, we have to use our gas law approach by starting with that big denominator line. And now, how do I get moles of ammonia? From our universal gas constant with moles in the numerator. But do note, this is from hydrogen information, so we're going to start with moles of hydrogen. So that's why I labeled it moles of hydrogen. Okay, that tells us where our temperature, our volume, and pressure need to go. And we have these values. Again, temperature always has to be in kelvins. But that gives us moles of hydrogen, so we're going to need to do one more simple conversion, and I hope by now this is a simple conversion. We go from moles of hydrogen to moles of ammonia using the balanced equation. And when I put this all on my calculator, I come up with 22.60 moles of ammonia that could potentially be formed from the hydrogen. So how much ammonia can I actually form? The lesser amount. The least amount is limiting me to this as the maximum amount that I can form. I might have enough hydrogen to form all that extra ammonia, but I don't have enough nitrogen. And now I have what I came for. Let me plug that into my original equation. And let me push those buttons on my calculator. And I come up with 82.1 liters of ammonia. We're still not done. What's last? And it should always be last. Asking if our answer makes sense. And I'm going to say it does make sense. It definitely seems within a reasonable range compared to the other gas information. Okay, that concludes this lecture where we learned how the actual amount of gas, the number of moles of gas, relates to the pressure, the volume, and the temperature. And we saw the ideal gas law equation, PV equals nRT, even though we didn't use it. I hope that you'd rather use your units when you can, and I hope that you do in this class so that you get maximum practice with those units. Because units can be used anytime with other classes, with your chosen professions, and definitely within your real life. We learned about STP, standard temperature and pressure, where we have the molar volume of 22.4 liters per each mole at STP only though. And then we saw some additional gas law calculations that come out of this when we now have moles, such as molar mass, grams per mole, and density of gas, grams per liter. And then lastly, we visited stoichiometry because we have a new way to get to moles.